Bruno, good. I see you there. Excellent.
Good morning, Stephen.
Good.
How are you doing?
Not too bad. You're all set up?
Oh, yeah, I
Wonderful.
think so.
All right. Very much looking forward to the talk.
So just tell me when you want me to share my screen.
Of course. Yep. I'll just run through some early announcements, and then we'll switch over and I'll introduce you.
Amazing.
Put your screen up. Yep. Excellent. Okay, well, let's kick things off. So welcome to day 2. Oh, I started that with 2 seconds too early. There we go. All right. So welcome to day 2 of AI CRV. We had a really great first day, lots of excellent attendance, lots of people here in person, and also some really strong showings online. We had 2 really fun social events that I was at least. I'm not sure if there was one on the AI side as well. But for CRV, we had a nice virtual student session, a social after the posters, which was really a hoot. So thanks to the program chairs, Helga and Xiu-Chin, for putting that together. There was a quiz and winners. It was very exciting. Lots of good time we had. And then we had our in-person dinner last night as well. We had, I think, about 50 to 60 people there. Really fun to see those that were able to make it. And we certainly missed everyone who was online. So we hope we can do that with you next year. So we have 2 sponsored talks today. So we'll start this morning with Bruno Monsarrat from NRC. So he'll kick off the activities shortly, just as soon as I wrapped up my preliminary notes here. And then in the afternoon, after most of the sessions, we'll have Keith Long coming to us from Applanix Trimble. So he'll be presenting at 4:45. And then there'll be a short break after that before our awards session. So this will be the awards for both the AI and the CRV conference, covering things like best papers and dissertation awards and the like. So please stick around for those, especially if you're an award winner. So we hope to see you all there. We have 2 great keynotes lined up for the conference as well today. So in the CRV side at 11:10, we have Maurice Fallon from the University of Oxford. And so he's going to talk about multi-sensor robot navigation and subterranean exploration. And then on the AI side, we have at 12:30 Diana Inkpen. And so she'll be talking to us about estimating depression and suicide ideation levels from social media for the Canadian population, which sounds fascinating and also very important. Okay, so those are the bulk of the announcements for today. So hopefully everyone remembers the procedures. So once we've completed our first talk by Bruno this morning, you'll have the 2 breakout rooms, one for each of the conference channels. And so what you'll do is you'll go down to the bottom of your screen, pick the breakout room button, and then select which of the 2 rooms you want to join, either AI or CRV. And of course, you exit back out to the main room and then switch to the other one if you'd like to see one or the other session. Okay. So let's get rolling then. So we'll jump right into our first sponsored talk of the day. So thanks very much to Bruno Monsarrat, who's coming to us and representing the NRC Aerospace Research Center, where he is a team leader in automation, robotics, and intelligent manufacturing systems. He's currently leading a research group of around 20 people conducting research activities at the NRC in the field of robotics and mechatronics. So there's an emphasis there on roboticized manufacturing of lightweight structures as well as UAV-based robotics. He's also a member of the executive committee of the Canadian Aeronautics and Space Institute. So I thought I'd mention a few of the important things. And so with that, I'll pass it over to Bruno and look forward to hearing about all the great things going on at NRC.
Thank you. Thank you very much, Stephen, for the introduction. It's a pleasure for me to be with you today. The title of my presentation is around the topic of developing competencies of robots through 3D sensing and artificial intelligence. So it's a growing, those two elements of sensing and artificial intelligence are growing in several of our projects. And what I wanted to do is just share about some of the successful deployments of these technologies. So from NRC laboratories to in the field deployments, I'd like just also to highlight that I was not alone preparing these slides. I received great content from Jonathan Boisvert, who is a team leader at our Digital Technology Research Center, my colleagues Gabriel Côté, Amir Ali Maghami, who is a guest worker within our team, but a PhD student from the University of Manitoba, and Iraj Mantegh. So one slide about the organization. So I'm here to represent the NRC, an important research technology organization, close to 4,000 employees, and we are spread throughout the country with 85 facilities, 1 billion in annual expenditures, supporting business innovation, partly a federal public policy mandate, and advancement of scientific knowledge. The way I wanted to approach the presentation, I wanted to share with you through a few case studies how NRC developed vision and AI-based technologies have enabled some of Canadian robotics applications. So I wanted to target 3 sectors today. The first is space. And I wanted really to pay a tribute to these contributions. So it took place a few years back, but I really wanted to pay a tribute to my colleagues who made that important contribution to the Canadian Space Robotics Program. My second topic will be air, so UAV, aerial robotics, so AI-assisted detection, tracking, and classification on drone versus birds. We have several activities with other federal agencies on that topic. And I will conclude with the third part on some of the industrial applications where we have been using vision and AI to enable these applications. And I'll provide you an outlook on 2 important flagship initiatives that we are working on at the moment with important collaborations and federating also vision, AI, and robotics. So to start with the space, a first case study on space applications. So I wanted to, as I said, pay tribute to my colleagues, essentially led by François Blais a few years back. And I think it's a very important NRC contribution to the Canadian Robotics Program. And just to, for you who do not necessarily remind exactly what was the context, essentially, the mandate Canada received from NASA was to provide a sensor that could actually allow the acquisition of dense 3D images for in-orbit inspection and maintenance. So you see here on that image, a defect on a structure. So typically, a sensor should be able to provide sufficiently dense 3D images to be able to identify such defects. The sensor should be able at the time as well to allow dynamic tracking of objects for assembly, docking, and teleoperation, should be robust against detrimental effects of sun illumination and Earth albedo, and have a minimized number of mobile parts complexity and a reduced weight to meet space specification requirements. So the sensor that was developed by the NRC, the team of François Blais, I provided one of the references, there are many papers and conference presentation, is the so-called autosynchronous 3D laser triangulation technology that allowed through that autosynchronous nature to minimize the number of mobile parts, minimize the complexity, and increase also the accuracy of the sensor. It was because it was laser-based, it was very robust to adverse lighting conditions, and a low combination of imaging and tracking modes. So here you have an image of the sensor. It's a prototype developed at NRC at the time. You see the approach for raster scan, so typical laser triangulation, but the same sensor allowed very fast dynamic object tracking, pose estimation by projecting simplified Lissajous tracking patterns adaptive to the surface to allow that tracking. And just that video to show just a statuette held by a colleague where you see the Lissajous tracking mode at the beginning, and then there will be a rapid raster scan that you just saw. So now we have a dense image of the statuette, and then back to Lissajous tracking mode, where we see that real-time tracking and pose estimation, both position and orientation. And you see the performance at the time that was quite state-of-the-art in the table provided as well. So less than 7 milliseconds for a single target. So Just also to provide a little bit of the history of that technology. So it was transferred, when prototype had been demonstrated within NRC, it was transferred to the company Neptech, who actually developed the space certified evolution, different evolutions of the sensor of that autosynchronous laser technology. The first flight took place actually in 2001. And you see the sensor on the image inside the cargo space of the shuttle. And you see an image that was taken actually showing the quality and the density of the image of some of the details on Canadarm2 on the International Space Station. So that was the first flight. The sensor had an evolution actually following the unfortunate disaster with the Columbia shuttle. There was a requirement by NASA to actually being able to do in-orbit inspection of the tiles underneath for heat protection underneath the shuttle. And actually that technology, the LCS autosynchronous laser, was actually part of the vision technology at the end of that 50-foot extension at the end of Canadarm that was used in actually a number of missions until 2007. And it actually prevented any issue with the thermal protection. And then there was another evolution of the technology. Neptech actually combined the autosynchronous laser technology with LiDAR to actually offer the TRIDAR rendezvous and docking navigation technology that has been used for ISS and shuttle navigation on 3 different missions until 2011, which was actually the last mission for an American shuttle. And after that period, actually that technology was encapsulated into a line of products commercialized by Neptech, the Opal sensors for navigation, and it has found multiple terrestrial applications in the air, on the ground, and so on. So something I wanted to highlight, there has been a number of application combining robotics and vision even before that, but I think that one is certainly worth mentioning. My second part about aerial robotics technologies, it's a growing activity within my team. And just an example that I wanted to highlight in that talk, essentially we have been working following the request from a number of OGDs in Canada, correctional services, DRDC as well, to actually come up with some robust technology for object detection and classification at far distance for small targets, being able to differentiate between drone and birds. It is a well-known problem. It is known that flying birds have similar radar cross-section at far distance than birds, same velocity range. So this is a challenge to do the separation between the classes. So this is a work we have been doing in collaboration with, you have the reference here, with the University of Ottawa, the team of Professor Bolich. And the approach has been twofold: to fuse AI classifiers on the radar side, the right-hand side. I will not present it because it's subject of a current patent application, but we are fusing that with a classifier on the video side using the PTZ camera data, which is the motion is due to the radar track, and we have synchronized AI deep learning approach for the optical detection. So that's what I wanted to highlight in that presentation. The development is summarized here in terms of the optical classification methodology. We have been generating ourselves through different missions using these sensors, over 5,000 images of target classes used for training that we have combined with a public data set to generate 116,000 frames with an important number of background images as well. We have pre-trained the network with YOLO v5 algorithms that we have selected for the PNet capability for instance segmentation, detection of small targets. And we have run it on 4 Tesla supercomputers from Compute Canada. And it took 24 hours for 32 epochs. You have some of the technical information just to tell you that the training data, the actual training data was generated with two types of drones. You have a DJI and an Inspire model, two models, an Echodyne and an Obsidian radar, with also more than 5,000 radar tracks that were generated to represent a good sampling of flying scenarios that have been used. So, and just to summarize the results, we have tested the approach using the IEEE VSS 2021 drone versus bird challenge dataset. You see a little bit of the results on the image, where we have shown that the ability to actually detect at far distance, even with very different backgrounds. You see here cloudy backgrounds, different illumination scenario. Here you see presence of an insect, so there is a robust detection of the drone in presence of other small objects. You see a case here with multiple drones. Also a case where you see the shadow of the drone on the building, so the shadow was ignored and the actual drone was well detected. The tree canopy at the back, and again the detection of the drone, multiple drones, and so different scenarios with improved detection up to 98% confidence. The remaining portion is really at very long range, where this is where especially the fusion with the two classifier, the video classifier and the radar classifier. The radar classifier is really helping, and we are combining both to improve the robustness of at very long range. Just to mention to you that we are advancing the technology. It's currently at TRS 7 with OGDs, mainly Corrections Canada. There is a big issue you're certainly aware of drone contraband delivery around prisons in Canada. So that's an important topic of research for us, and DRDC as well for defense applications. So I provided some of the references around that work. NRC is active on a number of topics, counter-drone detection, as well as obviously we are doing quite a bit of work on the navigation and collision avoidance as well. You can find a number of references as well if you're interested. Jumping to the third part of the presentation on industrial applications, where we have a growing use of metrology and AI technologies. Just to provide you a little bit of context in terms of how we approach the deployment of robots in industrial application. We are looking at process development, developing digital twinning with dynamical simulation of the robot, the processes. We do optimal synthesis of industrialization scenarios to maximize the productivity. We also use virtual commissioning infrastructure with actually controller in the loop simulation. All are important research topics. Today, I'll focus on just these two that I have highlighted on accuracy management and improvement of robots. These types of industrial robots are very good at being repeatable, but they have poor absolute accuracy. So we have developed methods for very high accuracy robot metrology guidance. You will see an example, geometric calibration, elastodynamic calibration methods, and the idea being to be able to do real-time model-based path compensation using real-time sensor data. Other topics that I'm mentioning here, but just I'll be focusing on these two. When I'm mentioning accuracy management and process competency development, we are doing it at 3 scales. There is an intersection between aerial robotics research and actually process robots. We are actually investigating the deployment of robots using UAV on difficult to access areas. So you see one of the prototypes where we are docking on a windmill blade, and actually we are developing an ultra lightweight robotic arm. So that's one area of development. The second is collaborative robotics payload from 3 to 30 kilograms, where these robots have the ability to work let's say, in the vicinity of human workers with limited, let's say, inertia that limits their ability to hurt humans. And then obviously the third class industrial robots, that this is what I'll be talking today. So before I jump to a multi-robot scenario, just showing some recent results actually that we produced in recent weeks. Until recently, we have been for single robot and multi-robot geometric calibration, we were using model-based approach. And through a collaboration with a PhD student, Ali Maghami from the University of Manitoba, we have investigated the use of machine learning for robot calibration. So you see the methodology. We are measuring a number of several hundreds of configuration using a laser tracker. You see the laser tracker target on the measurement end effector. From that measured data, we have found that it would be extremely helpful to go through a purification of the data, an outlier search in the joint space, to remove through a nearest neighbor algorithm. We're able to actually detect outliers. We are removing just maybe around 2%. And by doing that, we have a significant increase in the performance. After removing the outliers, we separate the training data, into training data, and we keep test data for the final model evaluation. That training data is going through a repeated k-fold cross-validation. I will be showing some of the result of that analysis. And to generate the best hyperparameters, retrain the model, and with all the training data, and do a final evaluation using the test data. You see the structure, the input are the robot joint angles, the output is the flange error in orientation and position. So some recent results, quite interesting. You see the cross-validation was run on 3 NVIDIA RTX 3090 GPUs. Hidden layers, we optimized and came up with 2 hidden layers, 256 neurons each, a batch size of 32 and 1000 epochs. With these hyperparameters, interestingly, the best in-class robot calibration software that has been used so far in the robot calibration community was producing, with the same data, 77 as a micrometer as mean error and 196 as max error. That trained neural network with optimized hyperparameters is doing better. 60 micrometer as mean error and 153 as max error. Quite impressed that the neural net could actually capture certainly more signature than what state-of-the-art model-based calibration was able to do. So at the moment, we are extending these results to multi-robot systems. And to talk about some in-the-field deployed NRC technologies, this is a system that you see quite nice. 2 master-slave robot manipulating a tooling. This technology was developed and deployed within the Saint Laurent facility of Bombardier Aerospace for the production of 5 panels of their Challenger 300 business jet. And actually, I want to quickly show you, I'm aware of time here, so but a quick video of it so that you can see the system has been in production for a few years now. The system is actually manipulating toolings. What's interesting here is that you would see infrared diodes on the tooling. The system is actually guided by an optical triangulation system in production. There is air pulsing around each of the diodes to make it robust to contamination in production environment. I will talk to you about the master-slave tracking error. I won't go through the whole video because of the lack of time, but just to show you that in each configuration, the system is actually drilling. There is a sealant application and a fastener installation, close to 3,000 fasteners per aircraft. So 11 fasteners per aircraft. So a good team joined with Bombardier, a joint development with Bombardier experts as well. A number of enabling technology, I will highlight a couple with you. Metrology guidance, you see the optical triangulation system, measuring diodes. We have developed an optimization tool in CATIA Delmia, allowing to synthesize the optimal scenario with minimum number of infrared diodes and optimized position of the sensor. We have 3,000 points, 4 diodes to be seen in each configuration. It's quite a complex problem. We end up with around 25 diodes per tooling, so quite a very optimized design. And you have diodes, fixed diodes on the drilling area. You see the result of that guidance. Before we had error up to 8 millimeters, because they are lever arm up to 4 meters between the master robot and the the farthest point on the panel. Under guidance, we are within plus minus 300 micrometer of accuracy. So quite impressive, and it's very robust to change in temperature and so on. A couple of interesting development to highlight. We have been using the same optical triangulation system to actually calibrate a model for master slave tracking error. Before the calibration, we have errors up to in position up to 18 millimeters of amplitude, which was a no-go. We developed, I will show you briefly, a calibration filter at the time using stochastic interpolation, using the measured data, using that optical triangulation system, reducing by eliminating 81% of the maximal error for all the trajectory points. So this is what has been used in production. Recently, we have been exploring the replacement of these 4 surface interpolation models where we were measuring at the different nodes that you see on the panel. You see the representation of the filter here. The predicted filter for all the trajectory point is the curve in black. So you see it's predicting errors of quite a significant amplitude. Now we have tried to replace those 4 dedicated filters by one optimized neural network, and this is what you see in green. Actually, with optimized hyperparameters, we have been able to show that the neural net could actually, with one neural network, we will have quite equivalent performance to replace the stochastic filters being used in production. At the moment, we are evaluating the impact of a reduction of the training data. We would like to reduce the 600 measurement configuration required at the moment to, let's say, 200 to 300, at least divided by 2, to reduce the calibration cycle time.
Right.
That calibration needs to occur every several years.
Thanks, Bruno. I think we have to wrap up here, if that's okay.
And that's perfect. I had a couple projects. I won't go that. We have a number of initiatives at the moment in the area of robotics, in the area also of manufacturing, multi-robot manufacturing of thermoplastic aerostructures. Just to tell you that we are eager, we are collaborating with a lot of university partners, international partners such as DLR in Germany. We have a number of international collaboration, very eager to collaborate. If you feel you're interested in these topics, we are really willing to expand our collaboration. So don't hesitate to approach us. We have very exciting projects to collaborate with you with. So thank you for the opportunity to present today, and I'll be pleased to answer any question you have.
Wonderful. Thanks so much, Bruno. So if anyone wants to join, you can give a quick round of applause. So that was really nice to see all the impact on Canadian industry and in robotics. So across such a long history, really, really nice talk. We're going to let people go straight on to their sessions. Unfortunately, we're a little bit over time, and I don't want to delay the rest of the conference. So those of you that are heading to either AR or CRV, find your buttons in the bottom of the breakout room. And again, Bruno, thanks for such a great talk.
Thank you. So any question also, don't hesitate to reach out directly to me. Absolutely. You can contact me. I'll be pleased to continue the conversation. Excellent. Thank you again.
All right. Take care, everyone. We'll see you in the session.
Thank you.